Hey, Algebra 2, let's look at lesson 23. We're still talking through rational expressions. Today we're going to be comparing them. See which one's bigger, see which one's smaller, etc., etc. So first of all, you were not given slips of paper, but we are going to use virtual slips of paper to create visual arguments for whether 1/3 or 3/8 is larger. Okay, one slip of paper I'm going to cut into thirds. And the other one I'm going to cut into eighths. Let's see, half, fourth, eighths. They're not perfect, but we'll get the point. And I'm going to shade 1/3 here and 3/8 here. Okay, sort of hard to figure, but which one is larger, the 1/3 or the 3/8? Technically, 1/3 is going to be smaller than 3/8. But it's sort of hard to figure out when your denominators are not the same, how to compare which one's which. You know, the other thing I could do is change each one into a decimal. 1/3 is the same as 0.33333 repeating, and 3/8 is the same as 0.375. So that'll help us see which one is smaller. But what if we don't have a calculator? You know, how does that work? How about if I put them both over the same denominator of 24? I don't know why I wrote 25 there. Over 24. 1/3 is the same as 8/24, and 3/8 is the same as 9/24. Okay, that's probably the easiest way to figure out your solution without using a calculator or without drawing pictures, especially if your pictures are not very accurate. Okay, let's try something else. Let's start by working just with positive integers. We're going to talk about m and n, and they always have to be positive. So let's work through these following exercises, sort of alone, alone in a way. Let's fill out the following table, okay, sort of simple. Got 1/2, 1/3, 1/4. Didn't you wish math was always this simple? Of course, if you love math, then you probably wish it was a little more difficult. Okay, so do you expect 1/n to be larger or smaller than 1/n plus 1? Do you expect 1/n to be larger or smaller than 1/n plus 2? So if we look at the table, 1/n, okay, it decreases, right? Okay, this means that since 1 plus n is greater than n, then 1/1 plus n is actually smaller than 1/n. Okay, to say it again, I have 1/n is bigger than 1/n plus 1 is bigger than 1/n plus 2, etc. Okay, let's try the next question. Okay, compare the rational expressions 1/n, 1/n plus 1, and 1/n plus 2 for n equals 1, 2, and 3. Do your results support your conjecture from exercise 2? Revise your conjecture if necessary. So let's look at n equals 1. I have 1/1, 1/2, and 1/3. So 1.5, 0.333. Definitely bigger going this way. Okay, let's try n equals 2. 1/2. 2 plus 1 is 3, and 4. Okay, we're definitely going bigger this way again. How about n equals 3? Okay, still. Okay, so therefore, 1 over n is bigger than 1 over n plus 1, is bigger than 1 over n plus 2. Moving on. From your working exercises 1 and 2, generalize how 1 over n compares to 1 over n plus m, where m and n are positive integers. So, really, since m is a positive integer, being added to n, the denominator will in fact increase. Which will decrease the value of the rational expression. So we have 1 over n is going to be bigger than 1 over n plus m for positive integers. Oops, forgot an I. M and n. Okay, let's try one more question. Will your conjecture change or stay the same if the numerator is 2 instead of 1? Make a conjecture about what happens when the numerator is held constant but the denominator increases for positive numbers. Okay, that means our numerator is now 2 instead of 1. It's going to stay the same because this would be the same as multiplying the inequality by 2. When our original equation was, so we're multiplying the whole inequality by 2. So the overall inequality is held. It's still greater than, you're just increasing the scale by a factor of 2. So if the numerator is held constant and the denominator increases, you're dividing by a larger number. So you get a smaller number overall. Okay, let's try another example. Suppose we want to compare the values of the rational expressions x plus 1 over x and x plus 2 over x plus 1 for positive values of x. What are some ways to do this? You can look at a table like we did before, which we're going to do now. So we're trying to compare these. What else could we do? Let's see, we could graph them and compare what happens. That would be difficult. Let's just go ahead and start with the table. So let's fill out our table for x plus 1 over x and x plus 2 over x plus 1. Okay, let's try this first one first. 1.5 over 0.5 is 3. Oops. 1.5, that's 3. 1 plus 1 is 2 over 1 is 2. 1.5 plus 1. I assume you're working along with me. Divide by 1.5. I've got 1.67. 3 over 2 is 3 halves. Let's keep it all in decimals. 6 over 5. 5 plus 1 is 6 divided by 5. I've got 1.2. 11 divided by 10, 1.1, and 101 divided by 100 is 1.01. Looks like my values are getting smaller as time goes. Let's try the next one. 0.5 plus 2 over 1.5 gives us 1.67. 3 divided by 2 is 1.5. So let's see, 3.5 divided by 2.5, 1.4. What's next? 4 divided by 3, 1.33. 7 divided by 6. 1.17. 11, nope, 12 divided by 11. 1.09. And 102 divided by 101. All right, so from the table of values, it looks like x plus 1 over x is greater than x plus 2 over x plus 1. So for all positive values of x. However, we've only checked 7 values of x so far, so we can't say this is the case for every positive value of x. How else can we compare the values of these two expressions? We said last slide that graphing might be an option. I would do this with my graphing calculator, not by hand, and I've got a picture of it on the next slide. Okay, if you look here at the graph, so it seems as though from the table and the graph that we can tell which rational expression is bigger than the other, but it's not a conclusive answer. How can we use algebra to determine if this inequality is always true? If you look, x plus 1 over x always seems to be bigger than x plus 2 over x plus 1, but we're still not really conclusive because we've only checked a very small set of numbers, of x's. So let's look again at just regular numbers. So I have 3/8 and, 2/7. Let's see what we can do with these numbers. We're going back to some pre-algebra maybe some elementary school math, but let's try to find our common denominator first. I can't find anything very small, but I know that 8 times 7 is 56, and 56 is a pretty easy common denominator to come up with. So 8 goes into 56 7 times, 7 times 3 is 21, 7 goes into 56 8 times 2 is 16, and now with a common denominator, we can easily see that 21 is greater than 16. So 3/8 is in fact greater than 2/7. And that's without using a calculator, without doing any division, etc. So the process for comparing rational expressions is the same as the process for comparing fractions. As is always the case with inequalities, we need to be careful about changing the inequality if we multiply or divide by a negative number. If you remember, if we multiply this whole thing by a negative, we have negative 3/8. We have to flip the inequality is now less than negative 2/7. It's just how it works with negatives. If you multiply or divide with a negative, you need to flip your inequality. So let's look at our rational expressions. Okay, we have x plus 1 over x and x plus 2 over x plus 1. We need a common denominator. And x plus 2 over x plus 1. Your denominator needs to have each piece of the denominators in it. So I have an x and an x plus 1. Just like with the last example, we had an 8. Goodness, that's an 8. When we were comparing just the two fractions, we had an 8 and a 7 in the denominator. We just had it because it looked like 56. Here we have an x and an x plus 1 in the denominator. Okay, so let's get our numerators. For this first one, I already have an x, so I just need an x plus 1. Okay, with the second one, I already have an x plus 1, so I need an x. Okay, that's how we're comparing. I'm going to do a little bit of multiplication. X squared plus 2x plus 1, and x squared plus 2x. I mean, if we just compare what's equivalent, that has an extra 1 on it, so the left side is going to be greater than the right. Okay, so x plus 1 is greater than x plus 2. X plus 1 over x is going to be greater than x plus 2 over x plus 1. Okay, since x is always positive, we know that the denominator x times x plus 1 is always positive. So we see that we can keep it on. So therefore we established, go back to the beginning, that x plus 1 over x is greater than x plus 2 over x plus 1. So for rational expressions, numerical and visual comparisons can provide evidence that one expression is larger than another for specified values of the variable. However, finding common denominators and doing the algebra to show that one is larger than the other is the conclusive way to show that the values of one rational expression are consistently larger than the values of another. All right? Okay, in closing, we're just going to do a side-by-side comparison of the different methods for comparing rational numbers to the extended method using for comparing rational expressions. For rational numbers, we can look at them visually, use area models or number lines to represent fractions and compare their relative sizes. It's very difficult with large numbers. For rational expressions, use a graphing utility to graph functions representing each expression and compare their relative heights. It's easy with technology, but inconclusive. Okay, we can't account for every single x value. Rational numbers, numerically, perform the division to find a decimal approximation to compare the sizes. Okay, we did that with our fractions. Rational expressions, compare several values of the functions to see the relative sizes. Straightforward, but tells us even less than graphing. This is where we did the table. Okay, we only checked like 7 values. Then algebraically, rational numbers, find equivalent fractions with common denominators and compare their numerators. Okay, and then rational expressions, algebraically, find equivalent fractions with common denominators and compare their numerators. Best way, but special care needs to be taken with values that may be negative. Remember, our inequalities change when we mess with negatives. Lesson summary: to compare two rational expressions, find equivalent rational expressions with the same denominator. Then we can compare the numerators for values of the variable that do not cause the rational expression to change from positive to negative or vice versa. We may also use the numerical and graphical analysis to help understand the relative sizes of expressions. Okay, check with me on the problem set. I'm pretty sure I reduced the work. Okay, so don't start working. You can email me if I haven't gotten back to you yet, but there was a lot of problems for this. Good job today.